Okay, good evening, everybody. Welcome to another episode of Cosmos from Your Couch, brought to you from home offices and bedrooms across the Greater Toronto Area in Canada. Let me just turn down my Sorry about that. So my name is Michael Reed, and I am the Public Outreach Coordinator of the Dunlap Institute at the University of Toronto in Canada. And for this episode, we're going to be doing another Ask Us Anything with my three colleagues here from the University of Toronto, Dr. Suresh Sivanandam, Dr. Cameron Van Eck, and Dr. Elana McDonald. And so the purpose of today's event is for us to open the floor to absolutely anything you might like to ask about any aspect of astronomy. It's a big universe out there. We can't guarantee that we'll be able to answer questions about absolutely everything, but we're going to do our best. So as we go along, we hope that you will feel free to type your questions into the chat window beside the video on YouTube. And we'll pick them up there. We've got a few of them already from social media from beforehand, but please feel free as we go along, put your question into the chat window and we will distribute that to our experts. So to start things off, I'm going to ask each of our experts to begin by introducing themselves and telling me a little bit about what you do. So maybe we can start with Suresh.
Hi, everyone, and thank you for having me on this show. So my name is Suresh Sivanandam. I'm a professor at the University of Toronto at the Department of Astronomy and Dunlap Institute. And so what do I do every day? I manage projects. So I build astronomical instruments on large telescopes located around the world to study how galaxies form. And one of the key things in astronomy is developing the tools of new tools to do new research. And that's one of the areas that I work on. And to study galaxy evolution, we really need to look at the universe at different times, because when we look at the night sky, we only see what's happening at the moment and at some past history of time. We can't see how things change over time, especially for galaxies that are located billions of light years away. And so we have to kind of do a puzzle, look at different galaxies at different distances and different ages of the universe and piece together how galaxies come together and evolve with time.
Okay, wonderful. Thank you. Maybe Elana now.
Cool. All right. So my name's Elana McDonald. I work at the Department of Astronomy and Astrophysics at the University of Toronto as the, it's a long one, instructional support and observatory/planetary administrator. And so what that means is that I help administer some of the biggest undergraduate courses we have in astronomy at U of T, so courses that are 1,500 students. And I also work a lot doing education and outreach in the department, so designing and running planetarium shows, giving observatory tours, sidewalk astronomy, that kind of fun stuff. I did my PhD at the University of Toronto and I studied the ripples in space-time that come from two black holes that spiral around each other and then eventually merge, and those ripples in space-time are called gravitational waves. So that's my biggest area of interest in astronomy, but really I like all kinds of astronomy and I try to spread that joy to the world.
Wonderful. And Cameron?
Hi, I'm Cameron Van Eck. I work at the Dunlap Institute as a research associate. My primary research interests are in radio astronomy. I like to use radio telescopes to look at the material between the stars, what we call the interstellar medium. And in particular, I'm interested in the magnetic fields that exist between the stars. And so I use radio telescopes to try to make measurements of that to understand how those magnetic fields come to be, what they do, what their shapes are, such as that. And these days, I tend to do a lot of technical work as well. I'm working a lot on developing software for astronomy, developing new tools for astronomers to use, working on big data projects, working on reducing data using supercomputers and writing tools that can work with that.
Okay, wonderful. So that covers a huge amount of ground. We've got gravitational waves, black holes, galaxies, galaxy formation, the gas and dust between the stars, astronomical data processing techniques, radio astronomy, tons and tons of things. So if any of those are starting to spark questions for you, please feel free. You can type them into the chat on YouTube. I'm going to ask our speakers another question, and then maybe we'll start looking to some of your questions. So the next thing I want to know is, tell me about something that was very exciting that you worked on recently, maybe the most exciting thing. And so perhaps this time we'll start with Elana.
Ooh. Something exciting that I've worked on recently. So I haven't done a lot of research in the last few years, but one thing that really excited me recently was I got to develop the curriculum for a math camp where they were learning about how math and space relate together. So I got to design some new planetarium shows for that, and come up with all sorts of interesting activities for kids to relate how math and space are related to each other. So that was a lot of fun.
Okay, great. Suresh, maybe.
Yes, that's a great question. I think one of the exciting things that I've been working on recently with other students is building a new system, building something new in our lab. We have a lab at the University of Toronto, and what our lab is trying to do is trying to be able to make very sharp images of astronomical objects. And in order to do this, you have to actually use a lot of fancy optical technology called adaptive optics, which actually tries to correct for the turbulence in the Earth's atmosphere, which blur the light from stars and various other objects. So we've recently built a state-of-the-art adaptive optics test system in our lab, where we can actually introduce turbulence and try and take a picture of a star and really sharpen it up. And actually seeing that work in the lab environment after at least probably about 2 years of work of putting things together and writing the software was probably the most exciting thing I've worked on recently.
Wonderful. And Cameron?
One of the things that I find most exciting about the work that I do is working with new telescopes, new radio telescopes in my case. And in the recent years, there have been two that have really excited me. I did my PhD working with a telescope called the Low Frequency Array, LOFAR, which is built in Europe. And it's built out of over 100,000 individual radio antennas that are all collecting signals from space. And they're feeding those signals into a supercomputer, which processes them to yield scientifically interesting data. It's an amazing piece of technology, just all of the components that go together to make it work, and all of the signal processing, the electronics, and the software. And these days I'm working with a telescope in Australia called the Australian Square Kilometre Array Pathfinder, which is also brand new. It's an array of 36 satellite dishes working together to image huge swaths of the sky all in one go. And it's also an amazing piece of very modern technology.
Great, thank you. So we've got some real experts here in not only space itself, but how we develop the machines and the software that allows us to understand space the way we do. So if you have questions about that, we welcome those. So we have lots of questions coming in. So I'm going to jump right to some questions from the audience. And maybe I'll direct this one to Elana. The question is, why is the sun going to expand into a red giant at the end of its life if it's going to stop burning fuel? What's going to cause the expansion?
Great. So currently, our sun is at its core fusing hydrogen gas into helium gas. So at the core of the sun, there's these extreme pressures and temperatures that allow two hydrogen atoms to get squished together and become a helium atom, and in the process giving off a huge amount of energy. At a certain point, in about maybe 4 billion, 5 billion years, there's going to be such a huge buildup of helium in the core of the star that the hydrogen fusion reaction won't be able to happen anymore. So you'll have this huge buildup of helium in the core. This hydrogen fusion process will stop for a little while. The core will start to contract in on itself, and that will cause something to happen, which is that helium atoms will start to fuse together to become the next heaviest element, which is carbon. And in the process, push away the outer layers of the sun, releasing a huge amount of energy, which will cause the sun to sort of blow up into this big, huge red giant kind of star. So that's more or less what's going to happen in 5 billion years.
So maybe we can follow that up with the same person, Jasmine's follow-up question, which is, why do big stars have higher temperatures?
Ooh, that's also a good question. So very, very large stars have a much higher mass than lower stars, of course, which means that these big stars have a lot more gravity, which means that the pressures and temperatures at the cores of those stars are much, much, much higher. And so since the pressures and temperatures are much higher, those fusion reactions, the hydrogen being converted into helium, those reactions happen a lot faster. And so those huge stars burn through their fuel much faster than they would before. And so that means that they're much hotter. And it also means that they live much shorter lives. So a star like our sun will probably last for about maybe 10 billion years, fusing hydrogen into helium in its core, whereas a much, much, much larger star might only last 1 million years, fusing hydrogen into helium in its core.
Great, thank you. So we have a question specifically for Suresh here, and the question is, what are some examples of objects you've been able to see in high res? What has surprised you the most in what you've seen?
High res. Okay, that's a good question. I don't know about me personally. There are a couple things that we can do. Recently, we looked at centers of globular clusters. So these are just clusters of stars, thousands of stars, kind of similar to what Mike's background looks like, though that's not a globular cluster. So we looked at the very cores of these clusters to see how fast these stars are moving. And the reason you would care about that is to look for a massive black hole in the centers of these globular clusters. And we haven't found anything yet, but we've done some of the highest resolution observations of cores of globular clusters, and really looking very close to the center to see if stars are moving. Now, what surprised me question, I think way back several years ago, I helped build a camera to make high resolution images of star systems and search for planets. So actually literally trying to see if there's a planet near the star. We spent a lot of effort searching a lot of star systems. I think we looked at almost 100. We didn't see any, but I think around the same time, another competing group used a different telescope and a different instrument and found 2 planets orbiting around the star. And so we actually turned our telescope and looked at that same star system, which was not part of our original search. And sure enough, we actually saw the planets. And this is probably one of the first times people have actually taken pictures of planets orbiting around nearby stars. And I think that was probably the most surprising high resolution observations that I've been part of.
And if I can ask you a follow-up question, were you satisfied with those pictures of planets orbiting other stars? Are we done now?
Well, we're not satisfied, obviously. This field is just exploding now, and everyone is working really hard to improve the technology. And it's really a technology-driven field to try to take the highest resolution images with the telescopes that we have right now. So I guess in science, you're usually satisfied for a moment when you accomplish something like that, but then you're always looking at the later thing in the improvement. And so that's what we're working on.
Okay, wonderful. Thank you. So for those of you who are just joining us, please feel free to type your questions for our astronomers into the chat window on YouTube, and we'll try and get to them. I'm going to jump around a little bit in the questions to try and distribute them among our speakers, but I will cycle back to each of the questions as time allows. So don't worry if I miss yours right away. I'll pick it up again in a little bit. So this one is a radio astronomy question, so I'm going to direct it to Cameron. And the question is from Isabella Rivera, who says, in the book Contact by Carl Sagan, scientists use radio wave science for SETI and end up finding some, presumably meaning extraterrestrial intelligences. Do you think we could ever use radio wave science to discover other intelligent life?
Yes, absolutely. And that was a wonderful book, Contact by Carl Sagan. But absolutely. And the SETI project, the search for extraterrestrial intelligence, still continues on. And they are very active in trying to use radio telescope observations to search for the evidence of extraterrestrial life in the form of their radio broadcasts. It's still active. There have even been purpose-built radio telescopes for it. There's an instrument called the Allen Telescope Array in the US that was built largely for that purpose and is also doing astronomy at the same time. And so that continues on. It is a very challenging problem, though, in the sense that there are a lot of different factors that you have to sort of overcome. I mean, the sky is very big. There's a lot of different radio frequencies that you can search for. There are a lot of different ways that a signal could be encoded. And so searching for all of these things is, to begin with, it's a bit of a needle in the haystack problem. And then beyond that, it's also a huge computational problem of looking at all the possible ways a signal might present itself. So there's a lot of continuing work, and there's always the excitement that something might happen, but we're never quite sure if or when.
Wonderful. This is actually a problem I've given to my students just this week, where I've asked them to try and decode theoretical radio signals from another civilization, and we'll see if we can even, decode a message from one human to another, right? It's tricky. So we have a couple of questions coming in about gamma rays. These are from Sophie and Eric. Sophie says, what percentage of gamma rays does the atmosphere block? 90%, 100%? And Eric says, will my tinfoil hat block gamma rays? Asking for a friend. Does anyone want to jump in on gamma rays?
I could make a comment about what percent of gamma rays are blocked by the atmosphere. All of it. It's just too energetic to make it through our atmosphere. I think the very high energy stuff actually accelerates some electrons in the upper atmosphere, and that can be viewed by these special telescopes. There are these telescope arrays that look for these flickers of light from high energy particles and some gamma rays interacting with the atmosphere. And the tinfoil hat, probably not. If you had a gamma ray source right next to you, I probably don't think a thin sheet of aluminum foil will help you.
Not something I'm intending to try, that's for sure. Okay, wonderful.
Did the Incredible Hulk morph himself with gamma rays? I forget what it was.
I think maybe.
Oh, wouldn't try that at home, though.
No, don't try that at home. Okay, we've got some questions from Instagram. So this one, again, I'll throw this open to whoever wants to try and tackle it. If the universe is expanding, does new matter and energy have to be created to fill up the space?
I'd be willing to give this one a go, I think.
Give it a shot.
Although either of you are free to jump in at any time. So our universe is expanding, which means that matter in the universe is getting farther and farther apart, which means that as a whole, in terms of matter, the universe is becoming less and less dense. So we're observing distant galaxies moving far away from us, and the farther away they are from us, the faster they're moving away from us, which is how we know that the universe is expanding. However, there is this thing that is causing the universe to accelerate in its expansion called dark energy. And that makes it sound like we know what it is, but we really have no idea. And that is some sort of energy that is causing the universe to accelerate in its expansion. And I'm not sure about too much about the details of dark energy, what we know about it so far, but I do know that it's supposed to sort of remain constant in the universe. So as you get more and more space, the ratio of dark energy to everything else gets bigger and bigger. So that means that the universe just starts expanding faster and faster and faster and faster as time goes on.
Anyone else like to jump in on that?
Add more.
I'm going to ask a follow-up question then. So Tracy asks a very related question related to Elana's explanation, which is, what is the difference between dark energy and dark matter? We get this kind of question a lot, these two very confusing terms. We'd like to take a stab at that.
I can take another stab at it unless someone else wants to. But basically, dark energy is some energy source that is causing the universe to accelerate in its expansion. And we have, like, beyond that, very little idea of what it could possibly be. Dark matter, on the other hand, is something we have a little bit more information on. Dark matter is a type of matter that exists in the universe. So it has mass, so it acts under the force of gravity, but it doesn't interact with other types of matter, the matter that we see, in any way except for through gravity. So no electromagnetic interactions, nothing else, only gravity. And the reason why we know it exists is because we see situations where we observe matter that we can see moving in such a way that there has to be more mass than is actually what we see. And so that's what dark matter is some sort of invisible mass that we don't know what exactly the particle is that makes it up, but that it doesn't interact with matter in any sort of way except for through gravity. And it makes up a lot more of the universe than regular matter does.
I just add one other thing. I think one way to think of dark energy, which we really don't know what it is, we just see its effect, is it's sort of like the opposite of gravity. So it's operating in a way that it's, gravity wants to pull things together, things with mass, but dark energy is actually pulling things apart. And we don't fully understand the physics behind what could cause that.
Exactly, yeah.
Wonderful. I think that's a great way of thinking of it. One pulls, one pushes, if you like. Okay, we've got lots of great questions coming in. So I'm going to go back to, I don't know if anyone on our panel will be able to answer this one, but I'm going to try and we'll see. So this is one of the earlier questions, and it was, is Comet Atlas really breaking up? What does that mean for its visibility? Anyone here want to comment on Comet Atlas? I think this person may win a prize for stumping our astronomers. None of us are experts on comets in particular, but that's okay. We'll have to, this is from, I wish I could attribute it to this person's name. Their YouTube name is WW. So WW, I think you win the prize for stumping our astronomers.
Well, I don't know anything about Comet Atlas specifically, but if a comet were to break up, then it would make it much more difficult to see because it would be broken apart, and therefore not much would be left to reflect light off the sun for us to be able to see it.
Although couldn't it be, I don't know much about comets myself either, but couldn't it be more visible if it broke into pieces that outcast or something, and each one got a coma or something on it? I don't know.
Maybe it could be briefly more visible and then it would stop being visible.
Yeah, you stumped us. We're not comet astronomers, unfortunately. Okay, back to things that we do know a little bit more about, I think. So this one isn't quite phrased as a question. Maybe it's something that I'll get Cameron to start commenting on. And the topic is, there are news about observatories, maybe 200 of them around the world, that are closed. And maybe the video feed from the International Space Station is also closed too. I think this person is probably commenting on things to do with the coronavirus. Does anyone want to, maybe we can start with Cameron, but anyone who wants to jump in and talk a little bit about, the experience of doing astronomy while locked in your living room?
Yes. So yes, it's definitely the case that many observatories have shut down for the same reasons that most other endeavors are shut down in order to protect the safety of the people working there. Astronomy, as much as we love it, is not a critical, essential service to society in the short term. However, there are many observatories that are still running. Many telescopes are set up to be automated so that they can be run remotely. And so telescopes with that capability are able to keep operating as long as nothing breaks. And so I actually got an email just this morning from the team running the Australian Square Kilometre Array Pathfinder saying that their plan is to continue observing as much as possible in the short term until something breaks, so that they can get as much data sort of stored in anticipation that the telescope may break, but our computers will keep running probably longer. So we'll have data to process for the time being as needed.
I can make a few comments on optical astronomy, where a lot of times we actually have to travel to the telescope and work with an operator there to take the data that we need for our research program. And because of the current crisis, all of that has stopped. Pretty much most optical observatories are closed. And the result from that is a lot of our science programs are basically stopped, and we don't know how many months this will continue for. And the way that you get time on these telescopes is there's a period of time where you want to do an observation and you have to write a competitive scientific proposal, and a committee, an expert committee, gives you time on the telescope. So because of this current unexpected situation, I think a lot of astronomers will lose the time that they have received to use these telescopes. But I mean, that's completely understandable. And we have to try and work on any data that we have already acquired prior to the crisis, and do the science with that for now.
Wonderful. Okay, we've got lots more questions coming in. So let me see if I can, I'm not sure who will take this next one, so you can jump in. This is kind of any of you could comment on this. This is from Fahid, and the question is, we know that galaxies are moving. Does this mean that black holes within galaxies are also moving? I think people are bothered by this idea of black holes moving, right?
I could take this question. Yes, they are moving. The best way to look at it is a galaxy is a unit. So when a galaxy is moving, the entire unit is moving. And so it's kind of like a little universe. So if there's a black hole at the center of the galaxy and the galaxy is moving, a few hundred kilometers per second this way, that black hole will also move with the galaxy a few hundred kilometers that way. And the reason I say galaxies are their own little micro universe is because their gravity has basically created this space where as long as there's nothing nearby, not another nearby galaxy, the galaxy internally is unaffected. And it could have its own motion, like a spiral galaxy could be rotating around some axis, and as long as there's no perturbation, and if it's moving in one direction, it'll keep rotating as it moves along. So you can think of them as cars. If you're sitting in the car and you're driving, there's a black hole in the car, it's going to drive along with the car, and it's not going to move off and do something weird. So that's the best analogy I have, the car analogy.
Elana, do you want to jump in on this one? Or?
Oh, sure, yeah. So Suresh is right. Yeah, the black hole at the center of a galaxy would move along with the galaxy itself. But I should probably also say that there are lots of other black holes besides the supermassive black hole at the center of our galaxy that move around our galaxy. So when a very massive star dies, sometimes it leaves behind a black hole where its core used to be. And there are a whole bunch of those types of galaxies, or sorry, those types of black holes around our galaxy. We estimate there are probably, I don't know, millions of them. And they would all go around the galaxy just like every other star in our galaxy would.
Great, thank you. So again, I'm going to bounce around a little bit in the questions here. I'm going to skip to one that I think will be probably best for Cameron, which is, does the cosmic microwave background pattern have a wavelength dependence? If so, what does that mean, or what would that mean?
Ooh, that is a very good question, and one that I'm not completely confident I can answer, although I can speculate a little bit. And so we do know for sure that the cosmic microwave background as a whole has a wavelength dependence. It acts like it's effectively a form of thermal radiation, sort of heat radiation, which has a particular spectrum, sort of brighter at some wavelengths than at others, corresponding in general to a temperature of about 3 degrees Kelvin. And so there are the variations in the cosmic wave microwave background pattern are generally treated as temperature variations. And so the spectrum would change from position to position based on the temperature in that direction. But my expectation is that pattern, it will always be the sort of thermal temperature pattern with a slightly different temperature. And so the pattern as a whole, I would expect to remain similar as a function of wavelength. But at least that's always the way I've seen the data presented. I've not looked at the data myself.
Okay, anyone else want to jump in on that?
Yes, I think what Cameron said makes a lot of sense. There is one potential perturbation on that, and it's not directly related to the cosmic microwave background itself. It is the matter that is between us and the cosmic microwave background can actually distort the wavelengths of light coming from the background. And this is usually done by massive clusters of galaxies. It's called the Sunyaev-Zeldovich effect. Don't mind that, but what happens is you have these massive clusters of galaxies that are sitting between us and the cosmic microwave background, and the clusters of galaxies are surrounded by very hot gas. So when the light from the cosmic microwave background hits this cluster of galaxies, it interacts with the matter and changes its spectrum a little bit, and adding a little bit more energy to the light than it used to have. And so by looking at slightly different frequencies, you can actually spot these hot balls of gas surrounding clusters of galaxies as a way of finding them in the universe at over very distant, out to very large distances.
Thank you. So we have a question that I think will be near and dear to a lot of people's heart, but maybe Suresh in particular. It's from Carolina, and she asks, how important do you think it will be the completion of extremely large telescopes like the EELT?
Very. So in terms of the astronomy research that I'm doing, and in general, in many areas of optical and infrared astronomy, everyone is pushing towards these very large facilities. And what these extremely large telescopes can do for you is make extremely sensitive measurements that are several orders of magnitude better than anything that exists right now. If you think about it, some of the most scientifically productive telescopes that we have right now were built in the 90s. So the largest telescopes like the Keck telescope or the Gemini telescope, they were built in the 90s. And the innovation that's happened has been mainly replacing the instruments that go behind them. And now, if you want to go to the next level in astronomy, particularly in the visible and infrared astronomy, you really need a telescope that has 10 times the collecting area of existing large telescopes. And the way these telescopes provide very sensitive measurements is they allow us to see, make even higher resolution images of the sky, as well as collect 10 times more light from individual objects in the sky. So it really pushes visible and infrared astronomy into a whole other domain.
Suresh, do you want to comment on, what's an example of something or multiple things that we'll be able to do with an extremely large telescope that we can't do now, other than just see in more detail?
So I think there are a couple areas where I'll mention 3 areas. So nearest to us, I think extremely large telescopes will finally be able to look for planets that are at least take images of planets that are not much bigger than the Earth. So really pushing towards solar system like systems, which we haven't actually seen yet because it's just extremely hard at this time. Actually also search for biosignatures in the atmospheres of these planets. There'll be enough light that we can see from each individual planet. We can look at the spectrum of the planet and see if it supports life. So I think that's one of the most exciting directions, at least in the nearby universe. Looking further, I think we'll be able to see galaxies that we could never see before because they were extremely faint in the distant universe, and possibly resolve some of the earliest galaxies in detail. Some of this work will be done by the James Webb Space Telescope when it launches hopefully next year. However, the James Webb Space Telescope has got a telescope that's about 6.5 meters in diameter, but then we're comparing with another telescope that's 30 meters in diameter. So it's so much bigger that it collects far more light, and it's able to see down to very make much more sensitive images of the sky.
Wonderful. So we can look forward to really a new era in astronomy when we get all these extremely large class 30, 40 meter diameter telescopes built. Everyone
Definitely.
Watching can look forward to really, really fantastic new discoveries and new images. Okay, so lots more questions. I'm going to try and get to all of them, but we're going to jump around a little bit. So I think this one maybe is ideal for Elana. It comes from Isabella, and she asks, how do I make my little sister less terrified that a black hole won't tear us apart any second?
Ooh, okay. Okay, so black holes can be scary because they're these big weird objects in space. And if you got really close to one, it would be really dangerous. However, the closest black hole to us that we know of is several thousand light years away. And so even traveling in the fastest spaceship that we have, it would still take millions of years to get there. So chances of us running into a black hole in our own galaxy are pretty slim. So we won't crash into a black hole anytime soon, probably not even within the lifetime of our sun. So probably not within the next few billion years. So I wouldn't worry about that too much. Although now that we're on the topic, could I talk about what would happen if you did fall into a black hole?
Of course.
So the reason why black holes are so dangerous is because of something called tidal effects. So if you were to fall in towards a black hole, and let's say this is like the edge of the black hole right here, as you are falling in, let's say these are your feet and this where my wrist is would be your head, the gravity at your feet would be much stronger than the gravity at your head. And so that would cause there to be sort of a net force across your body. And so as you are falling into the black hole, you'd actually get stretched out a little bit. And the scientific term for this is spaghettification. So essentially, as you fall into a black hole, you'd get stretched out like a string of spaghetti, and then eventually get ripped apart and fall into the black hole. But as I said before, the chances of that happening are very, very, very unlikely. So nothing to worry about for us.
I think we want to end on a high note on that one so we don't leave Isabella's poor sister even more terrified. But I think just to flip around what you said that, you know, even in our fastest spaceship, it would take us a really long time to get to a black hole. But a minute ago, I'm pretty sure you guys said that black holes were moving around the cosmos all the time. So is a black hole going to come and get us?
Probably not, because if, say, they're about a few thousand light years apart, then the chances of us running into one are pretty slim. And even if they're moving around, the spaces between stars are so vast that we wouldn't be able to hit one, I don't think.
So certainly not in Isabella's sister's lifetime.
No, certainly not in any of our lifetimes.
Good. Okay. Lots more questions. So Vinita's asking some technical questions. This one is about galaxies. And again, I'm not sure who to direct this to, probably Suresh. I have another question about galaxies. How do you tell where the edge of one galaxy ends and another galaxy begins? Anyone can answer that.
That is a challenging question. It depends. A lot of times galaxies are living on their own. You know, they're not very close to each other. And in those cases, it's pretty obvious where one galaxy ends. You know, just take pictures of the galaxy, or if you're Cameron, take a picture of a radio image of the galaxy, and you can see the gas of the galaxy, and you can see where the edge of it is. Where it gets more tricky is if you have galaxies living in groups or clusters, and they're in these areas, they're very close to each other, and sometimes they're interacting. And when they start interacting with each other, then it becomes extremely tricky, you know, which galaxy is, you know, which part of which galaxy is where, and sometimes impossible to distinguish between the galaxies. But there are some ways to get around it. We can actually make measurements of motions of stars and gas in these different galaxies. And depending on which galaxy the star and gas is associated with, you might see slightly different motions. And then you can kind of separate out, okay, this one's moving this way and that one's moving this way. And even though they look like they're interacting or they're very close to each other, you can actually tell apart which galaxy is which and where their boundaries are. But it's a very difficult problem, and you know, honestly, if you go and read the literature, people are finding new and novel ways of making these types of distinctions.
We have an astronomer at the Dunlap Institute, Dr. Bob Abraham, who works on a telescope that he and his colleague developed called Dragonfly, which is optimized for taking pictures of galaxies that show, or other things that show the very, 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 very faint outer edges and things like that. So maybe we'll try and get him to come on for a Q&A sometime and maybe even show some of his photos. Okay, so there's a bunch of questions. Again, anyone can take this. So Ian asks, what are your ideas for a 5-year-old with an interest in astronomy and astrophysics? Someone has already suggested you should check out our sister project, Discover the Universe. You can go to their I'll post the link maybe, but you can go to their YouTube channel. They're running daily sessions for kids every weekday in both English and French on all sorts of topics in astronomy. So if you're still stuck in self-isolation, you can watch some of the Discover the Universe videos. But other ideas people have for a young person who's interested in astronomy?
Well, there are a lot of really excellent resources online, but one of my favorite things to do is to just go outside and look up at the sky and try to identify a few things. So this time of year, you can see the moon, of course. It's in a third quarter phase or close to that right now. So it's not visible until very, very late at night. But so you can look at the moon, you can look at what phase it's in, you can, look at it from night to night and see how it changes. And there are also a lot of planets that are visible right now. So if you look at the western sky after sunset, you see a very bright object, and you can actually see Venus. It's very, very easy to pick out. And then if you stay up really, really late, right now, I think it's Jupiter, Saturn, and Mars are all visible, rising in the wee hours of the morning, I think around 3 a.m. And so you can see all three of those in the sky right now. And they're bright objects that are visible even in a city like Toronto with light pollution. And so if you can figure out where those things are in the sky, then I think showing those to kids get them really inspired. And that was definitely one of the things that inspired me when I was a kid, was my dad pointing out to me, hey, that's Saturn in the sky. And then maybe moving on from there to look at some constellations, and like the Big Dipper, pointing that out, and Orion. So I think that that's a really fun thing to do with kids, is just to actually look at the sky and see what you can see.
To follow on with what Elana said, I think having a combination of, there are all these great planetarium apps, some of them are free, that you can download on your smartphone, using that as a companion when you're out with your 5-year-old trying to identify things, and you can use that as a reference to show what and identify things if you're not familiar with them.
I think a really great free resource for that is Stellarium. It's an app you can download either, I think it's on the phone and on your computer, and it can show you what the sky looks like at any time of night, any time of year, and that can help you locate where things are in the sky.
And that works anywhere on the planet as well, for those who are watching from elsewhere. Great. I think also one last thing I would add to that is that if you're in Canada, you can consider looking out for the local chapter of the Royal Astronomical Society, or in Quebec, the Federation of Amateur Astronomers of Quebec. And then elsewhere in the world, there are amateur astronomy organizations in just about every country in the world, and they often have programming that's suitable for younger people or less experienced observers. Okay, we have loads of questions coming, so let's try and get through a few of them fairly quickly here. So I'm going to try and pick one from someone who I don't think has asked yet. Heather says, because of the lack of black holes in our neighborhood, does that mean we're in a relatively young portion of space or of the universe? Oh, you've made them think, Heather.
I can offer a few thoughts potentially. So one of the things that I seem to recall about galactic dynamics, so the motion of stars, black holes, and other things through our galaxy, is that there's a fair amount of mixing that goes on over time, over periods of hundreds of millions to billions of years. There's a fair amount of mixing. So for example, groups of stars that get born together in a cluster can quite often drift apart. And that's a whole area of research of trying to reconstruct which stars were born as siblings, even though they're in maybe different parts of the galaxy now. And the same thing can happen with black holes. And I think one of the open research questions is actually, when a black hole is formed during a supernova explosion, can it get kicked away from its birth environment? So if that happens, it could pick up a velocity of maybe several hundred kilometers per second, which over the course of millions of years will move it quite far away from where the black hole was born. And so I don't think we can say anything about sort of the lack of local black holes in the sense of the question that was asked.
Yeah, I'd also like to add to that, well, a couple of things. First of all, the stars that can produce black holes have to be very, very massive. And very few stars reach that mass where they can become black holes compared to the masses of other stars. So usually, so in our galaxy, we have lots and lots of really low mass stars. We have a few that are a bit more massive, even fewer that are more massive, and very few relatively that are massive enough to, at the end of their lives, become black holes. So I would say that probably black holes are about evenly interspersed throughout the galaxy, but the chances of running across them are pretty low, just because compared to everything else, there isn't a whole lot of them. And I also wanted to talk about the age of our neighborhood. So we know at least that our sun is a probably third generation star, because of the amount of elements that we can see in its atmosphere. And so, we think that the very first generations of stars were basically just hydrogen and helium, and they produced elements that formed the next generation of stars. And then those stars created more elements that we see in the stars that we see in our local neighborhood. And so we think that, in our neighborhood, it's actually not newer than anywhere else in the galaxy, and probably pretty standard.
Wonderful. So we have a trio of related questions here. I'm going to maybe try and go through them one at a time. So the first one is, are we able to observe any constellation changing due to the movement of its stars?
I could probably answer that one too. So we haven't, within a human lifetime, we don't observe constellations changing, because stars in our galaxy are moving very quickly around the galaxy, but we're so far away from those stars that we barely notice that motion at all. It's sort of like if you see a train moving in the far distance, even though it's moving, at say 100 kilometers an hour. I don't know if trains go that fast, but if it's moving really fast, it looks like it's just crawling across the horizon because it's so far away. So we don't really notice within our lifetimes stars changing in such a way that we'd be able to notice differences in constellations. But we do know that stars do move, and that over tens of thousands of years, you would actually notice that the constellations change in the sky. So probably in the next 100,000 years, the Big Dipper won't look quite the same as it does now.
Suresh, did you want to add to that?
No, that was a
No?
that
Okay.
was a good explanation.
Okay, so then I'm going to give you the next two as a pair, and anyone can jump in on these. So Terry asks, how do you measure or determine the distance to distant objects? So say at 50,000 light years versus 1,000,000 light years, or how do you measure how fast the universe is expanding? And Annabella asks, what is the math involved in measuring star parallax? So these are both questions about measuring distance and motion of distant objects, and perhaps how that relates to the measurements of the expansion rate of the universe.
I could try and take a stab at this. Is a very great set of questions. First of all, I have to say that it's hard to do this over different distance scales. And the astronomers, we call this process the distance ladder, because depending on how far away the object is, you have to use a different set of techniques to figure out how to measure its distance from us. So the fundamental way to do the nearest objects is using parallax. And the way you do parallax is, you're basically using the motion of Earth around the sun, the different locations the Earth travels across, and you look at a patch of sky at 2 different times of the year, so maybe 6 months apart. And if the star is really close to us, it will actually seem to move with respect to the stars that are much further away. And this level of motion is related to how far away that it is. So we basically measure the angle that it moves on the sky, and there's a fairly straightforward geometric calculation you can do, which is related to the location of the Earth around the sun at the 2 different measurement points, and you can actually figure out how far away the star is located. Now, if things get far enough away, so this angle measurement is actually really difficult, because the further the object is, its parallax, or the change in angle, becomes much smaller. And it gets to a point where our scientific instruments can't actually measure the actual change in position. So we have to use other techniques to measure the distance. Within our galaxy, one way to do that is look at a given star at some distance, figure out what type of star it is, if it's a supergiant or very massive main sequence star. Then we can, from our models, ascertain how bright it should be and measure how bright it is when we actually receive the light. And as the further away an object is, it looks fainter, but if we know how bright it should be, we can actually estimate how much further away it is. Now, if you get much further away, there are other techniques like pulsating stars. Some stars pulsate over time, and these are called Cepheids. And when they pulsate, depending on how frequently they pulsate, you can actually figure out how bright they actually are. And then based on the brightness that we measure here, we can figure out how far away it is. And if you go even further, you start looking at things like what's called redshift. So when an object is moving away from you very quickly, the light from the object actually changes. The light actually gets redder if it's moving away from you. And the faster it moves away from you, the redder the light from the object looks like. And if you know some very specific features, for example, hydrogen lights up really well and has very specific emission lines, so you can fingerprint it. And then based on how red these emission lines look like, you can actually tell how fast the object, like a galaxy, is moving away from us. And that's predominantly how we measure very distant objects and how quickly how far away that they are from us. So there are many levels in the ladder.
I'd like to add to that, if I may, that one of the ways we measure the most distant things, as well as redshift, is also using a type of star explosion called a supernova, specifically a type 1a supernova, where you have a core of a dead star called a white dwarf that explodes in this huge cataclysmic explosion, which is, you can see from very, very far away. And it always reaches the same brightness. And so we can use that to calibrate how far away these very, very, very distant galaxies are. And it was actually using those exploding stars. We use that to figure out how far away very distant galaxies were, and use that to show that the universe was actually accelerating in its expansion, because the distances that these different galaxies were at were different than what you'd expect if the universe wasn't accelerating in its expansion.
Okay, wonderful. Thank you. So we're getting towards the end of our time. We still have quite a few questions people have asked, but I'm going to skip to a couple of the sort of follow-up ones, and we'll start with Cameron, I think, for this one. So I'm going to prime everyone for one of the questions, and then I'll get you to answer the other. So the one I'll prime you for is people would like to know, someone on Facebook wants to know, what's your favorite fact about the universe? But maybe before we do that, I'm going to ask everyone for recommendations for books for people who are interested in astronomy, or maybe for those who are new to astronomy. Cameron, do you want to start with either a book or a fact?
So the book question is rather difficult. I mean, I find as a professional astronomer, I'm reading a completely different class of books to what a member of the public would read. So I don't think I've purchased a sort of general astronomy book in many years, unfortunately. But in terms of, good facts, I'm biased towards facts related to my research. And so the thing that I love about the universe is that everything is magnetized, and yet it's something that we don't generally think about. I mean, the Earth is magnetized, we know that, but so is the sun, and so is the Milky Way as a whole. And that's something we don't tend to think about, but there's a magnetic field there, and it does some crazy stuff.
Okay, how about Suresh? A book or a fact or both?
I think any book by Carl Sagan on astronomy is particularly good. For example, like the Cosmos. I really got a lot out of that. But that's, I mean, if you want to learn astronomy, then I think I can't point you exactly to a particular book that I really like. There was, I think, a book called Universe. It's kind of a really large book, The Universe or something like that, which has a lot of pictures of a lot of astronomical objects, and it actually goes through a great deal of detail. And it's a very visual book, and I think if you want to visually learn things, that's a great way of looking at it. I don't remember the author of that book. I think it had an editor that put together all the images and explanations. So in terms of a fact that's a bit mind-blowing for me is, I think until recently, we didn't know that on average, there is at least one exoplanet per star within our galaxy. And that's just mind-blowing because there are billions of stars in our galaxy, and there's at least one planet orbiting around the star, and possibly more. And it just is mind-blowing because I feel like, and I'm a great sci-fi fan, I feel like there's got to be life, there's got to be a habitable planet somewhere within our galaxy, and it's just a matter of time before we find several of these. So that, I think that has been the fact that really excites me.
Wonderful. Thank you. Elana, book and fact.
Okay. Oh, it's so hard to just pick one. But okay, so my favorite book for beginner astronomers is the book that sort of got me really into astronomy, especially amateur astronomy, just looking up the sky and looking at stuff through a telescope. And that's the book Night Watch by Terence Dickinson. It's a really excellent beginner's guide to just the night sky and scales of the universe, and it has all sorts of really, really great pictures, and it's spiral bound, so it's easy, or at least the copy I had was spiral bound, so it was easy to lay out flat and to look at all the pictures when I was a little kid. And unfortunately, I don't have a copy of it here because I left it in my office at work. But yeah, it's a really, really fantastic book. And fact about the universe. I think that my favorite fact about astronomy that gets me really excited today is the fact that we can observe the universe in so many different ways and learn so much about it without actually being able to visit the whole place. So we can tell so much about distant stars and distant planets and all sorts of stuff that is millions of light years away, and even figure out how the universe was created, or not created, but how it started, just by looking at the light that comes from stars and from different parts of the universe. And now that we're observing stuff in gravitational waves, which of course is my favorite pet project of astronomy, is the fact that we can now look at things in space in many different ways. So you can look at the light coming from different objects in the universe, but now with gravitational waves, we can actually observe the actual ripples in space-time that are coming from different very massive objects. So I just find it so cool that we can, tell so much about the universe without actually leaving our little cozy planet Earth here.
I found the book. Does it show up?
You may have to turn off your virtual background, Suresh.
Oh,
it's disappearing into the bridge of the Enterprise. Or you can just tell us
the universe. I think it just says universe. The Definitive Visual Guide. That's the title of the book. And I'm a very visual learner, so I found it has a lot of pictures and great explanations from everything from within the solar system heading all the way out to the distant universe. So it just has a smorgasbord of stuff.
Okay, wonderful. Well, I'm afraid we've reached the end of our time. I know we haven't answered absolutely every question. There was a great one in there about magnetism that I wish we had a chance to hand to Cameron, but I believe the person who asked that has come to one of these before, and so maybe you'll be able to come again and we'll deal with some more magnetism stuff. Thank you everybody very much for coming. This has been our second Cosmos from Your Couch question and answer session. We're going to be having more of these periodically, so if you're interested in hearing more from another group of astronomers in a few weeks, please follow the Dunlap Institute on social media. We're on Instagram, Facebook, Twitter, and you can also go on the dunlap.utoronto.ca website and find the full list of upcoming Cosmos from Your Couch events. We have them twice a week, every week, and we'll be doing this at least as long as we're all in isolation and maybe more. So thank you very much. Thanks very much to all of our wonderful astronomers. Thank you to everyone who was with us for our hour tonight. And please keep coming back and we'll share more of our love of the cosmos with you very soon. Thanks, everybody.
Thank you very much.
Thank you and
Bye.
good night.
Have a good night.